Good afternoon. This is Kaylee Nelson with the Bureau of Reclamation. Thank you for joining us on this educational outreach session on the Colorado River Basin study. Because more than 100 people are joining the webinar, we will be muting everyone except for the webinar presenters. To ask a question, please type your question into the question box on the webinar toolbar. We will address questions at the end of the presentation. And now I'd like to introduce Carly Jurla, Reclamation's co-manager for the Colorado River Basin Water Supply and Demand Study.
Thank you, Kaylee, and thank you everyone for joining us here today for this webinar. Before we get started, I also want to recognize the study manager for our cost share partners, the 7 basin states, and that was K Brothers with the Southern Nevada Water Authority. So this is the final of 3 outreach sessions that we have been putting on, and the reason we are doing these outreach sessions is to provide the public an opportunity for a more in-depth understanding of the findings in this very complex and technical study. We have about a 3-hour webinar scheduled today. There will be 30 minutes allotted at the end for questions, and we will have a 10-minute break in between at about an hour into the study. And as Kaylee indicated, you all are on mute, and if you have any questions, please feel free to type those in, and we will begin answering those during our question and answer session. This is the agenda for today's outreach session. I will start with a brief introduction, then talk about the water supply and demand assessment portion of the study. I will then talk about the options and strategies that were explored in the study and the development of the strategies or the portfolios, which are groups of options. We will then break for about 10 minutes, and then Ken Nowak and Alan Butler, who were the technical leads for the modeling aspects of the study, will take over and present the system reliability analysis, both the methodology and the results, leading us up to really the open question and answer session, which will be about 2.5 hours into the webinar. The introduction portion of this session will be comprised of a short background on the layout of the Colorado River Basin. I will talk briefly about the Water Smart program. This is what the Basin Study program is a part of and what the study was conducted under. I will then do a broad overview of the Basin Study and talk about the objectives and the phases that that the study was laid out in to accomplish those objectives, and then briefly talk about the final report and how to comment on that report. So as many of you know, the setting of the Colorado River Basin. It's approximately 250 square miles. It spans from the headwaters of the Green River in Wyoming down to Mexico. The study area, the area of which the study is conducted over, is defined as the hydrologic boundaries of the basin and those adjacent areas that receive Colorado River water. And those adjacent areas are denoted on the map in the red hatched areas. The annual allocations in the basin do exceed the basin's long-term average flow. That long-term average flow has been about 15 million acre-feet over the past 100 years. We're going to use the term natural flow a lot when we're talking about the supply on the basin. And that term really means what is the flow into the basin had humans not existed. So without the impacts of humans depleting the flow or any reservoir regulation on the system. We talk about the term Lee's Ferry a lot also when we're measuring the total flow on the basin, and that's a point just below Lake Powell where about 90% of the flow in the basin culminates at, and that's a really good measure of the total flow in the basin. So you'll hear that term a lot as well. Those flows are highly variable, and we'll see that in figures in a couple slides away. And due to the storage that we have on this system, the ability to store 4 times that average annual inflow, or about 60 million acre-feet, that storage has provided us flexibility in meeting those demands. The system has worked really exactly as it has been designed. We've been able to store water in high flow years to meet demands during the lower flow years. And because of that, we have essentially made all of our delivery commitments despite having a pretty severe drought on the basin over the last 10 years. The system is managed in accordance with the law of the river. This is a compilation of documents dating back to the 1922 Colorado River Compact. And this law of the river is constantly evolving and is what we manage our system under. This figure shows the historical annual basin supply and use over the roughly last 100 years, so dating back to 1914. The blue line is the annual water supply. This is a measure of total basin supply, and the red line is the annual basin water use. So this is a measure of the total use on the basin. You can clearly see that the use has been on the increase really since the last 100 years, while the supply has been very variable. There have been many years in the past where our use has exceeded the supply, and as I mentioned previously, due to our reservoir storage, we have been able to meet deliveries during those periods despite that imbalance. If we look at the 10-year running average of these two lines, so this is the same data we looked at in the previous figure, but we're now looking at the 10-year running average to better see the trends. You can clearly see use is increasing while supply has really started to decrease in the last 10 years. That's the recent drought we've been experiencing. And we have really surpassed the supply over the last 10 years. And we know that we are currently in an imbalance in this system. And as we move forward, and really the purpose of the study is to see how those supply and demand curves are going to change moving into the future over the next 50 years. The Reclamation's Water Smart initiative puts into place many different activities that allow us to conduct studies that are going to look at these types of issues. The Water Smart initiative puts into place authorities set forth in the Secure Water Act. The Secure Water Act was passed into law on March 30th, 2009. And this statute establishes that Congress find an adequate and safe supply of water to meet many of the fundamental things that water is essential for, and to do so considering the impacts of global climate change. There are three major programs that are in place to tackle these issues. The Basin study deals with risks, impacts, adaptation, and mitigation strategies, and is looking towards feasibility type studies after the completion of a basin study. So underneath that basin study program, the Colorado River Basin Water Supply and Demand Study was conducted. The objective of the study is broad, and this is same for any basin study that's conducted under this program. The objective is to assess future water supply and demand imbalances over the next 50 years in the basin, and to develop and evaluate opportunities or options and strategies for resolving those imbalances. Every basin study has a cost share component, so it's conducted with stakeholders throughout the basin. This basin study was conducted by Reclamation and the agencies representing the 7 basin states. It was roughly equally cost shared, and those cost share partners are listed in the table there on the right. But it was also conducted in collaboration with stakeholders throughout the basin. Many Native American tribes and communities, conservation organizations, recreational organizations, and others were very involved in the study, and their involvement was critical to the success of the study. Study was about a 3-year effort. It began in January of 2010, and it was completed in December of last year. And the study is exactly that. It's a study. It does not result in any decisions. It is not a NEPA analysis or an EIS. There is no recommendation on how to move forward to resolve future imbalances. Its aim is really to provide a technical foundation for future activities and for future discussions to build upon. The study consists of 4 major phases to accomplish the objectives of the study. In the first phase, which is the water supply assessment, we're looking 50 years into the future and projecting what water supply might look like on this basin under a range of different future scenarios. In the in phase 2, the water demand assessment, we're doing the same thing except for demand. We're looking 50 years into the future, trying to understand how demand under many different sectors may be changing on this basin. In phase 3, we bring those projections of supply and demand together to understand how the system reliability changes under those scenarios. And this is understood by first identifying what we call system reliability metrics. System reliability metrics, these are things that are going to indicate how well the resources that the system operates for are performing. Once we understand how well the resources are performing, then we can think about different opportunities to enhance the performance of those resources or resolve those supply and demand imbalances. And we do that in phase 4, beginning with the development of those opportunities, testing the effectiveness of those against how well system reliability improves, and then the finalization of those opportunities. The study had a consultant team that consisted of CH2M Hill and Black & Veatch. These consultants were brought onto the study early on in April of 2010 and really provided the overall support for the study, as well as bringing technical assistance to the supply and demand assessment and the other components listed here. They also provided technical integration across all aspects of the study and documentation support. Early last year, the RAND Corporation was brought on really to provide support for the system reliability phase of the study and also the vulnerability assessment and the portfolio development and evaluation, which we will get into a little later in the session. The final study report is really a collection of reports. There are 7 technical reports, A through G, that are going to cover roughly in about a total of 1,500 pages, all technical aspects of the study. Those 1,500 pages are summarized in a 100-page study report, which also contains a discussion of the next steps after the study. And then there is a much shorter 20-page executive summary that will summarize each major technical finding in the study. All of those documents are available for download up on our website, and we are also happy to provide CDs of the documents at request. You can request one of those CDs and also submit comments on any of the details found in the study by the website or email listed here. We are asking comments to be submitted by April 19th, and there's a variety of ways to submit those comments. What we plan to do with these comments is to summarize them and post them to our website and use these as we move forward, both in next steps after the study, but in future basin planning activities as well. So that covers the broad introduction into the study. I'm now going to shift into the water supply assessment. This was the first phase of the study. I'll talk shortly about the objective of this phase, and then talk through the development of our water supply scenarios and then the quantification of those scenarios. The objective of the water supply assessment was to assess the probable magnitude and variability of both the historical and future natural flow in the basin. And as I mentioned before, natural flow represents the flow that would have occurred at a location without the impact of human depletions or reservoir regulation upstream of that location. This assessment includes the potential effects of both future climate variability and change. Because we wanted to look very broadly in terms of what future supply might look like on the basin, we identified 4 different scenarios. I'm going to step through the scenarios one by one, and as I do so, think about how each scenario sort of expands the range at which supply may evolve in the future. The first scenario is called observed resampled. What it does is resample through the observed historical record as an indication of what future hydrology might be like on the basin. So the idea behind this is really history repeats itself. The figure here is our natural flow record at Lee's Ferry. It's dating back to 1906. You again can see the variability from extreme low years in 1977, for example. Our natural flow was barely above 5 million acre-feet, to some of the years during the 80s where we were reaching 25 million acre-feet. This water supply scenario, observed resampled, is really saying that the next 50 years will be identical to the last 100 years. Each supply scenario consists of multiple different sequences for future stream flow. By doing this, we're able to get a distribution of how supply may play out under a certain scenario. So to get a distribution, assuming the history repeats itself, we resample through each one of this past record to get 103 sequences of future stream flow. This record is 103 years long, so we can get 103 sequences of future stream flow. To expand the range of to expand the range of how hydrology may play out, we've added to the supply scenarios the paleo resampled scenario. So this is relying on the tree ring records that are reconstructed for the last 1,250 years to give us an indication of what future stream flow might look like. We are able to generate 1,244 sequences of future stream flow in this scenario, and the figure here is showing you the 25-year running average of this historical paleo record. So it's dating back to 762. There's 2 different reconstructions, both done at the University of Arizona by Dave Miko and Connie Woodhouse. And then the lime green portion is showing what the last 100 years have been relative to the last 1,200 years of the paleo reconstruction. That dotted lime green line is where our recent 25-year average is. And you can see that that's a pretty low average even by measure of what we've seen in the last 1,200 years from the paleo record. To expand that range a little more and to think about more extreme drought spells or different surplus spells than we've even seen in our historical or the paleo record, we introduce a third water supply scenario. It's called paleo conditioned, and it's really blending both the historical supply on the basin with the paleo supply on the basin. The approach here will give us 500 sequences of future stream flow. Finally, we want to look at what happens if temperature and precipitation are much different than what we've seen in the measured past. What is common through the previous 3 scenarios we just looked at is they're all assuming a stationary climate. And we want to expand the range even more by looking at what happens if we find ourselves in a future with changing precipitation and temperature much different than what we've seen in the past. So we introduced the downscaled global climate model projected, or downscaled GCM projected scenario. To get this scenario, we utilized 112 projections from global climate models. under 3 different emission scenarios. These were bias corrected and downscaled for precipitation and temperature. We took that precipitation and temperature and moved that through a hydrologic model to get projections of stream flow, and then we can use those 112 sequences of future stream flow to understand the impacts on the system. We're now going to look at a summary of the quantification of those different scenarios. So the figure here is showing you the distribution for each one of those scenarios, with the history repeats itself scenario on the far left in the blue and the climate change scenario on the far right in the red. And we're looking at the distribution of the future long-term averages, so 2011 to 2060 natural flow at Lee's Ferry. If you focus on the observed scenario, you can see that the median of that distribution, which is indicated by the triangle, the orange triangle there, is right at 15 million acre feet. So that is what our historical average has been on this basin. So it would make sense that the statistics you see for the future long-term average wouldn't be much different than what we've seen in our past historical long-term average. If you move, then follow the line, if you follow that 15 million acre feet where the median is of the observed all the way to the right for the climate projection statistics, you see that that triangle is a bit lower. It's sitting at about 13.6 million acre feet, and that's about a 9% decline from that 15 million acre foot average. So you definitely are seeing a decline in the long-term mean from the historical average, but you're also seeing the biggest spread is indicated by the width of that box in terms of the variability around that number. And at the 25th percentile, we are just above 12 million acre feet as a long-term future mean. The dotted line here indicates what our recent 20-year average has been on the basin. It's been at about 13.6 million acre feet, which is about where we find the median ending up at for the climate change projection. If we think about future drought and surplus statistics, what we found in these different scenarios is if you define a deficit period as a period when the 2-year running mean is below the observed mean of 15 million acre feet. We want to look at a 2-year running mean here because we all know on this basin and the variability that we see, 1 year of good flow doesn't necessarily break a drought spell. But in defining a deficit that way and a surplus is just the opposite, we're seeing that the frequency of those events occurring, ones occur that last 5 years or longer, happen much more frequently under the climate change scenario, and that's 48%, and it's circled there. If we look at surplus frequencies, 5 years or longer, we see the most frequent occurrence of those being under our history repeats itself type scenario, and less than 1% if we're looking at the downscaled GCM projected scenario. I'm now going to shift into the results of the water demand assessment. These results are highlighted and much more detail is provided in our technical report C. I'll talk basically the same structure as through the water supply, talk about the objective, the development of the scenarios, and the quantification of those scenarios. So the objective of the water demand assessment was to assess both the quantity and location of both current and future water demands within the study area. So again, the study area is defined as the hydrologic boundaries within the United States plus those adjacent areas that receive Colorado River water. And approximately 25% of the water in the upper basin is exported to these adjacent areas, and it's double that in the lower basin, about 50%. So understanding demand in these areas is critical to understanding the total demand placed upon the Colorado River. Resources that we have included in both the assessment of demand and in the system reliability analysis, which we'll look at a little later, include municipal and industrial use, agricultural use, hydropower generation, recreation, and fish and wildlife habitat. We developed 6 demand scenarios that indicate how demand may evolve under changes in different driving forces on the basin. And the way these demand scenarios were crafted was through a multi-stakeholder team that really thought about the different driving forces that would influence the way demand might change in the basin. And those types of driving forces include population, water efficiency changes, changes in irrigated agriculture, changes in water demand for energy, changes in water to meet tribal needs, and so on. So this group thought about different pathways that these driving forces could take and then weaved these pathways together into storylines. What's shown here is really the brief version of those storylines, and we have 6 different scenarios that came from these storylines. The first is called current projected. This is really your kind of middle of the road, business as usual type demand scenario. We're looking at medium growth, medium changes in population projections, and development patterns and institutions that continue along recent trends. At a much slower pace, we have the slow growth demand scenario. This has a much slower rate of growth in terms of population with an emphasis on economic efficiency. So there is not the economic environment for the adoption of a lot of new technology in this demand scenario. In rapid growth, we're really looking at the complete opposite. There's an economic resurgence of both population and energy needs, energy demand to meet that population growth. And that is coupled with 2 different branches for how technology may evolve, a slow technology adoption and a rapid technology adoption. And this has current preferences towards human and environmental values. And that will make more sense once I talk about the last 2 demand scenarios. This is in the enhanced environment scenario. There's 2 branches here. And so this is looking at preferences towards environmental values that are different and more expanded than what we see in rapid growth. And we're expanding that environmental awareness and stewardship along with a growing economy, and we're coupling that with both a moderate population growth in D1 and a rapid population growth in D2. And this really translates into the rate at which we adopt new water efficiency technologies, and that expanded environmental awareness results in a much greater adoption of some of those technologies. So how do we take these storylines and come up with quantified demands? We do so in the approach described here. So we begin with that storyline, and we have all of the different driving forces or parameters that comprise that storyline. And each one of those parameters impacts a different category of demand. So for example, if we're looking at agricultural demand, that's impacted by irrigation efficiency and irrigated acreage. We put numbers to each one of these parameters or driving forces. The numbers were provided by both the basin states, but also through by various tribes and environmental organizations involved in the study. As we put numbers to these, we can quantify what the study area demand is, and then to back into what our Colorado River demand is, we need to make some assumptions about what some of those other supplies may be providing. So this is really how we deal with some of those adjacent areas that are outside of the basin that receive Colorado River water, but also rely on other sources to meet the demands within that area. There are assumptions that are made about these other supplies to arrive at the Colorado River demand, and after implementing these assumptions, we result in a quantified demand scenario. This figure here shows the results of those quantified demand scenarios. We're looking at both historical use on the basin, which is in the left since 1970, and then added on for the future part of the figure, so from 2012 to 2060 is those future demand scenarios. The demand scenarios are bracketed by the slow growth and rapid growth scenario, that's in the orange and the red. There's about a 20% spread in the change in demand between those two scenarios. And it's roughly from about 18.1 million acre feet under slow growth to 20.4 million acre feet by 2060 under rapid growth. And this is when you factor in the treaty delivery to Mexico and losses on the system due to reservoir evap or evapotranspiration losses to native vegetation.